All right, so in this section, we're going to divide monomials. Now, when we multiplied monomials, we kind of went to houses, we worried about the creepers, and we're going to be putting all that together with division. Except in division, you're going to have two-story houses. So what's going to happen in division? You're going to have a problem up on top, a monomial on top, and a monomial on the bottom. So for example, if you had x to the 7th on top and x to the 3rd on the bottom, that means you've got 7 x's up on top and you have 3 x's on the bottom. 1 and 1 and 1 all cancel, so you end up with x to the 4th up on top. You could have a 1 on the bottom, but we're lazy and we don't write that. So what you're really doing here with your powers is you are subtracting the exponents. These are the two questions I ask myself. Where are there many, where are there more, and how many more? Because wherever there's more, that's where you're going to end up with the ones left over, because the rest of them are going to cancel out. How many more means you're going to subtract. How many are going to be left after you cancel all of them out? Sometimes they'll be on the top, sometimes they'll be on the bottom. So for example, if I change this problem and put x to the 4th on the top and x to the 7th on the bottom, I have 4 x's on the top, 7 on the bottom. Boom, 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 leaves me with 3 x's, but it's on the bottom, so I'd have to put a 1 up on top. You have to have you have to have something on the top. You don't have to have the 1 on the bottom. You can leave that off. But if it's on the bottom, if your x is on the bottom, you got to have the 1 up in the numerator, okay? You're going to deal with these just like you did the regular houses. Numbers are going to take care of themselves. X's are going to take care of themselves. Y's by themselves. Z's by themselves, or whatever. Everybody's being separated by their own little house. We also have a rule, the zero exponent rule, and anything to the 0 power is 1. Let me show you why. You might have learned that a long time ago. Maybe they never told you why. Let's go to x to the 4th over x to the 4th. Do you agree that that equals 1 in disguise? Because it's the same number over itself, right? Well, let's write it out. 4x is on the top, 4x is on the bottom. I have 0 x's left. Or if I subtracted, 4 minus 4 gives me that x to the 0. So anything to the 0 power equals 1. We also have a rule called the negative exponent rule. If you have a variable to a negative power, and remember that would have been over 1, because if there's no fraction bar, that means the denominator's 1. That means you take that variable, you move it from the top down to the bottom, from the numerator to the denominator, and make the power positive. If it starts out negative in the denominator, you move it up to the top, that's really over 1, remember, and make that positive. The only other thing I don't have written here, let me go ahead and show you what the other thing that could happen. You could have an entire problem to a negative exponent out here. What that means is, because the negative power is outside, you got to move the x squared to the bottom, you got to move the y cubed to the top, and then the power becomes positive. So if an entire fraction has a negative power, you flip the fraction and make it to a positive power. We're going to see all that in our examples. So the first example, if you look at this, I wish I could highlight. I probably can. I'm probably just not smart enough. So if I look at this, I've got these numbers, 4 over 8. Remember what numbers tell us to do? They tell us to go to a calculator. So if I reduced 4 over 8, it would be 1 over 2. So that's the fraction part. You just reduce it. You don't do any subtraction. You don't do anything weird. Those are rules for powers or for exponents. For numbers, you just follow the number rules. So the next thing I've got that I'm going to look at are these x's. And what I've got, so in my little head, I'm looking at x to the 3rd over x to the 5th. Where are there more x's? On the bottom. How many more? Well, I'm going to take x to the 5 minus 3. 5 minus 3 is, whoops, that was supposed to be black. I hate that when I do that. X to the 2nd. Okay, remember 3x is up on top, 5 on the bottom. 3 cancel, leaves me with 2 on the bottom. Next, I'm going to look at the y's. So now in my head, I'm looking at y to the second over y to the cubed. Where are there more y's? On the bottom. So subtract. 3 minus 2 is y to the first. So what's on the bottom? A y. I don't put that one because I'm lazy. And the last thing I'm going to look at are the z's. Now I've got z to the second on top, z to the second on the bottom. Where are there more? Nowhere. What would I do if I subtracted them? 2 minus 2, which is z to the 0, which is 1. So I just leave them off. They're gone. So my final answer is 1 over 2x squared y. When I go to this second example, I remember that dear woman. She used to buy me such a great birthday present, my dear Aunt Sally. Please excuse my dear Aunt Sally. The P right here, this P stands for parentheses. So inside the parentheses, I'm going to take care of the problem. So I'm going to put parentheses, big old long line parentheses, and put the squared out there. I'm just setting the problem up. I'm not dealing with that squared outside first. What I am going to look at is 2 over 3. Does that reduce? No. So leave it as 2 over 3. I'm going to look as x squared over x. Uh-oh, that x doesn't have anything, so I put a 1. So when I subtract x squared over x to the first, x to the 2 minus 1 is just x to the first. This time I'm going to put it there because I'm not done with the problem yet. For my y's, I've got y to the third over y squared, more up in the top. So I'm going to subtract to the top. That's going to leave me with a y to the first up on the top. Z over z, that just cancels because they're the same. Now what I'm going to do is I'm going to go back and I'm going to use those creeper rules. Remember we said everybody gets the creeper if it's inside the house. So 2 gets squared, x to the first gets squared, y to the first gets squared. Those are all up in the numerator upstairs. In the bottom I have a 3 and it's getting squared. 2 squared, go to your calculator. 2 to the second power is 4. Power to a power, old rule, we learned it last time. It's multiplication. 1 times 2 is 2. Power to a power, old rule, learned it last time. Multiplication. 1 times 2 is 2. In the denominator, 3 squared is a number, so I just take 3 and I square it, which means 3 times 3, which is 9. And that's going to be my final answer. Okay, looking inside the parentheses, there is stuff I can do, so I'm going to set it up again. 3 over 5 does not reduce, so I'm going to leave it 3 over 5. I'm going to look at the x's. I've got 2 x's on the top, 3 x's on the bottom. There's more x's on the bottom, and 3 minus 2 is 1. All I have for y's is just one little old y. I'm going to give him that 1, leave him up in the numerator because that's where he started, that's where he belongs. I don't want to move him around because there's nothing else weird on it. Now I'm going to take care of that outside creeper. 3 has a power of 3. Y to the first has a power of 3. In the denominator, 5 gets the power of 3, and x to the first gets the power of 3. 3 to the third, go to the calculator. 3 times 3 times 3 is 27. On the y, power to a power, you're going to multiply. So it's going to be y to the third. In the denominator, 5 to the third, go to your calculator. 5 to the third, 5 times 5 times 5, 125. For your variable of x, you have a variable base of x. 1 times 3 is 3. If you have simplified inside the parentheses and you've simplified correctly, you should not have to do any reducing or any simplifying at the very end. You should be done. So the next one, what I'm looking at now, big old parenthesis with an exponent of 4 outside. For my numbers, I've got negative 2 over 4. Go to the calculator. That reduces to negative 1/2. This is the only x term I have, so I'm going to leave them where it is. And then my y's, I'm going to put a 1 on that y. I've got y, 1 y on the top, 2 y's on the bottom, so they're going to end up on the bottom, and 2 minus 1 is 1. Then I've cleaned up inside, so I'm ready to go to the power outside. So I have negative 1 to the 4th, x to the 4th, take it to the 4th, all over. 2 to the fourth, y to the first to the fourth. -1 is a number. Go to your calculator. -1 to the fourth comes out to +1. This is a variable, so I'm going to multiply my powers. 4 times 4 is 16. 2 is a number. Go to the calculator. 2 to the fourth is 16. Y is a variable, so I'm going to multiply my powers, and it's going to be y to the fourth. Do I need the 1 on top? No. I could get rid of it, or I could leave it there. Or I could get rid of it, or I could leave it there. Your choice. Okay, now, these I'm going to play a game called Stay or Move. Before I do anything else, I'm going to play the Stay or Move game. So I'm going to rewrite the whole thing, and I'm going to ask each factor if it stays or moves. When does something move? When it has a negative power. Negative numbers exist. Negative powers cannot. So 3 is just the number 3, it stays. X to the fourth, positive power, it stays. This y to the -2, negative power, so I'm going to move it to the bottom and make it a +2. So I've taken care of that one, that one, that one. 9, regular old number, don't even move numbers. Numbers just stay where they are. X to the -3, whoopsie doodles, it's got a negative power, so I'm going to move it to the top and make the power positive. Y to the third, it's got a regular old positive power, so I leave it there. So the ones that move are the ones that have negative powers. If it was a negative number, it stays. Negative powers. Powers have the power to move, okay? Now, look at this problem. 3 over 9 reduces to 1 over 3. When I look at my x's, they're all up on top. So I don't subtract, I add. It's x to the 7th. Remember, I'm multiplying this x times x. Multiplication used to be written like that. That's kind of a sideways plus sign. Division is written with something on the top and something on the bottom, and that's just a division bar without the dots, which is a subtraction sign. So multiplication, you add. Division, you subtract. The y's are all in the denominator. They're all together. I'm not dividing, I'm multiplying them. So I'm going to add the exponents and I'm going to get 5. This last example over here, I've got a lot of guys who have to move. So I'm going to set it up. First thing I'm looking at is x to the -4. Whoopsie doodle, negative power, move it to the bottom. I look at this y to the -7. Whoopsie doodles, negative power on top, move it to the bottom. I look at this w to the 3rd, positive power, leave it where it is. And this z to the -1, whoopsie doodles, negative power, move it to the top and make it positive. Can I put anything together? No. I've got a z, an x, a y, a w, nothing multiplied or divided that are the same, so I just leave them. Sometimes it looks better if you drop that 1 and then you put the denominator in numerical order. Doesn't really matter. Either answer is okay. Last example is a little bit different. We said we do the parentheses first, but the problem with this one is I have 2 separate sets of parentheses. The top one's being taken to the -2, the bottom one's being taken to the 2nd. So I'm going to deal with this top first. Inside, so I'm not looking at that right now. Inside, is there anything I can do with 2x to the 2nd, y to the 3rd, z? No. I have 1 letter of x, 1 y, 1 z, 1 number. So now I'm going to look at that -2. Because the whole thing is being taken to the -2, I'm going to move the whole thing to the bottom and change that outside power to a +2. This one down here, 3xy² z, nothing I can clean up inside. It has a positive power already, so I'm going to leave it down in the bottom with the positive power of 2. When there's nothing up top, you have to put a 1. So now I've got this 1 up in the top. This one says I'm taking 2 to a power of 2, x² to a power of 2, y³ to a power of 2, z to the 1st to a power of 2. This one has 3 to a power of 2, x to the 1st to a power of 2, y squared to a power of 2, and z to the first to a power of 2. Holy moly, that's a long fraction, isn't it? Do you have to do that? No. Is it safer to do that? Yes. So I've got 1 up on top, 2 squared, 4. X squared squared, multiply x to the 4th. Y to the 3 to the 2nd, multiply y to the 6th. Z first to the 2nd, multiply 1 times 2 is 2. 3 to the 2nd, numbers, 3 to the 2nd is 9. Go to your calculator. Here I have x to the 1st squared, multiply 1 times 2 is 2. Here y squared squared, multiply 2 times 2 is 4. Here z to the 1 squared, multiply 1 times 2 is 2. Why do I go to those new rules? Because my base is a variable. If my base is a number, I just use number rules. If my base is a variable, I have to use my exponent rules. So I've got 1 over, I've got 4 times 9, those are my numbers, bring them on home. I've got x to the 4th, x squared, y to the 6th, y to the 4th, z to the 2nd, z to the 2nd. All I did was bring them on to their own homes. I just had to keep them under the denominator. 4 times 9 is 36. Now I'm adding because I don't have a power to a power. Power to a power is going to have a parenthesis in between it. When I just have x to the 4th, x squared, I'm going to add. So that's x to the 6th. Adding y to the 10th. Adding z to the 4th. And that's your final answer. So how do you know when to multiply and how do you know when to add? That's kind of confusing. One thing I look at, let's go back to this. Let's look at this y one. Y cubed squared. I only have one y. That's a hint. I also, when I look at my two powers, I have a parenthesis between them. Parenthesis means multiply. But when I have this and I look at my two powers, there's nothing between them, so I'm going to add. Gets a little confusing. Try these over and over until you're comfortable with them. Good luck.